Good afternoon. I'm here today to talk about a Motorola project where we developed a system to automatically identify battery-related bugs on smartphones by just using the log files. In this project, I take part as a researcher, but outside the Motorola's lab, I also do a few other things. I am a master's student at FEC Unicamp, working on Bayesian deep learning, and I am co-founder of Datart, a data science consulting startup. So if you have any interest in these topics, please come talk to me later. So before I go into the specifics of how we tackle this problem, let me give you a context. When Motorola creates a new smartphone, a new product, we do a process called dog fooding. Dog fooding is where a bunch of Motorola employees use these new smartphones before it's released to the market. So the dog fooders try to report all the bugs that they may find, suspicious behaviors, so the developer can provide a fix for this problem. And when the majority of these bugs are corrected, this new product is released to the market. But not all the bugs are perceptible to the final user. So we cannot only rely on them to report this kind of bug. So we do a more automated process where every day in the smartphone of the dog fooders we collect a bunch of logs. Then these logs are analyzed by a triage team that read these logs, try to find evidence for a bug, and when they find enough evidence, they send these reports to a developer to provide a fix for this problem. But there is a bottleneck in this process, and here it is. We have more reports being created each day than the triage team can analyze. So just a few numbers, we have more than 300 reported created each day, and the triage team can analyze only half of these numbers. But this is just the first problem. The second problem is that only 30% of these reports are actually bugs. So most of the time of the triage team is spent in reading logs that are not that important. So with these problems, we set up two goals. The first goal was to create a system to automatically read a log and identify if it has a bug or not. And we can use this system to automatically close reports that don't have bugs. And we can prioritize reports that have a high probability of having a bug. And our second goal is to improve the time that a triage team analyzes a report. So, for instance, we want to give hints for where to look at it in the logs so they can accelerate this process. So now we can go into how we tackle this problem. Here is the data. There are a bunch of logs, more than, I think, more than 10 log files with more than 1 million lines. But there are two special ones, the ones the triage team used to find evidence for a bug. The first one is the battery tracer. It's a time series file with more than 100 variables, and the second one is the Android bug report. It's a pretty standard log file in the Android community. Probably the most important information in these logs are the summarized data. And in the time series, you can find, for instance, how much Wi-Fi was transmitted at each time, how much current is passing in the battery, and so on. in the bug report, the summarized data, you can find how much time the screen was on, how much the screen was off, or for instance, how much data was transmitted to the radio. From these files, we extract a bunch of features. Unfortunately, I don't have the time to talk all the history here, but this is just the happy ending. From the BTD time series, we extract pretty simple statistics like mean, standard deviation, max, mean, skewness, and a lot of statistics. In total, we have 65 features from the time series. And from the Android bug report was the file that take a lot of months to crawl entirely, because it's not a structured file. This file has different versions, so we had to detect each version is that file, so we can extract the information in the right place. And from this file, we extract 200 features. These features, as you can see in the end, after 31 versions of these features, they give pretty much the same result. They work best, obviously, when they are concatenated. So we have to choose one of these, and we apply Occam's razor here, the simplest one. The one that only depends of the bug report file, because the BTD file, the time series file, they cause a large overhead in the smartphone to collect. So, and the Android bug report is a more standard tool in the Android community. So we choose to extract features only the Android report and remove the dependence of the BTD. So classifiers. This was the most easy choice we have to make. No one was able to beat XGB here. So, and just to give that 1 or 2% more, we try a few stack arrangements. The final winner was a stack of 10x extreme gradient boost with extreme gradient boost in the top. So this is an interesting, it's a business restriction that was imposed to us. We had to comply with the 2 restrictions. We have to less than 10% of false positives and less than 5% of false negatives. False negatives are when our models say that it's not a bug, but it actually it is. So when a false negative happens, it's more costly to the company, because a bug it's going to production, and the false positive ones are less costly because they only cost time of the triage team. So they will spend just a few minutes to analyze a report if you classify wrongly. So with this model, here is the production results. We run our model for 3 months in background just to see how it performed. In these 3 months, our 26,000 reports was arrived to our servers, and only half of this number was actually analyzed. And we use these analyzed reports to see how our model actually behaves. We had 95% of AUC with an overall accuracy of 91%. And while complying with the business restriction. Here, when the community of machine learning, I see a lot of mistakes being made with evaluation out there, because, for instance, in our setting, time is a really important thing, because at 1 week we can receive a new bug, a bug that was our model was not trained on. So it's also important that we detect this kind of bug. We want to predict new bugs. And what I see, right, in the wild, people getting the entire data set, shuffling, and split and train and test and evaluate in your test. But when you shuffle your data set, you are giving your model information about the future. But this will not happen in the production, so you have to really be careful about this. So in our setting, we sort our data set by the time that the report was created, and we split in weeks our training. We split in weeks our data set, and each week we separate to predict and use to train our model only the past data. This is the same result as before, but here is by week. So it was also important that our model were stable over the time. So you can see most of the time it's complying with the business restriction. Besides, we have two outliers here, but this was not a problem. With this model, we achieve our first goal. We have a pretty good model to predict if there is a bug or not in giving a report. And our second goal, a much more challenging one, explain what the model is doing. And our first try, obviously, is get the most interpretable model that exists, a decision tree. And we use this decision to explain what the model is doing. We get each path of the tree and translate this path to a natural language, because the humans were not comfortable with just giving the variables and the thresholds. So it was important that we translate this kind of this path to a human language so they can be comfortable with. Our second attempt to do explanation, we take the human justification for a bug or not, and we clustering this justification and select the few keywords. So these keywords we use as label for training. So we use our features that we extract from the logs, and we label it with the keywords that we extracted and classify these keywords. So just to finalize, a few things that we learned from this project. Please don't try to use deep learning or whatever you need, or whatever you think when you don't need it. Start with a very simple baseline, like a linear regression, a mean, for instance, and then you improve on that. The second thing, that if your machine learning case are not working, probably the problem is not the model, it's the data that you are trying to fit. For instance, try to collect the data more recent, do some some sampling your data set and checks if the labels are correct. It estimates the noise in the labels, and it spends some time trying to do feature engineering. It has a large payoff. And the final thing, don't underestimate reproducibility, because most of the time, from time to time, try to reproduce all the results that we had, so that probably you find a lot of errors that you have made in the past. For instance, check your calculation of your metric. Be careful to not leakage your model, and so on. I think that's it. Thank you.
Thank you, Ramon. We have time for some questions. Yep, one back there. Hi, thanks for the talk, very interesting. I had a question on the evaluation that you did. So this was for one of the dog food campaign. Do you believe the model will be stable if you apply it to a new campaign, if you release a new product?
Yes, that result for models, for new smartphones were testing at the same time. So these are all the results for models. For new devices, and I think two different Android versions, M and N, at the same time. We do not split the model by the new for each different smartphone. We test that, and it not give better results.
Okay, more questions? Hey, here.
Do you have some information on how much cost do Motorola reduce it in the analyzing the reports? And if you have this information, this volume of cutting the cost in analyzing bugs, what is this compared to your false negatives when your bugs are not detected and are put into production? And actually, it was really good. You have a good model, but you have 10% of false negatives.
False positives, I think. Yes, false positives are not a big concern, because we don't want to replace the triage team. We just want to help them, to improve them, so that the time they already will spend. So our model is just cutting some triage in the backlog they were having.
Okay, one more question here.
Okay, congratulations for your presentation. So I have a question here. Do you have an idea why the LSTM performs so badly in comparison with the extreme gradient boosting? Especially when correct me if I'm wrong, but at the start of your problem, you are dealing with time series problem, right?
Yes.
So do you have any kind of
the problem? That's an interesting question. The problem is that our time series has more than 5,000 steps. So LSTM probably cannot memorize all the steps they have to make. We try to group time to have a shorter time series, but it does not work for us.
I have another question there. Then, if you have time, I'll go back here.
The thing about battery that I believe as a user is that the perception of the user is it can be more important than the raw data that you have. So in fact, you get more pissed off with the battery when you really need your smartphone and you are on a dark street or something. And do you have any tests on the last end with the user perceiving it, the battery and so on? Have you tried something like this?
I don't know if I understand the question, but this is a very hard thing to evaluate, to measure. But most of the case, probably the final user will not perceive the battery drain. For instance, most of the errors occur when they turn off the screen. So they put in the pockets and the applications keep running. So this drain your battery, but the final user doesn't know why, and they don't report this kind of error.
We have a follow-up question here.
Okay, yeah, it's on the LSTM. Did you you say that you have the problem with the steps back, right?
Yes.
Okay, did you try to use some classical statistical models like Karima, like Garsh, and so on?
Yes, we try to use auto-recursive models, but the things that we perceived is that summarized data are already good to our problem. So we from the time thing was not a factor in your problem. In the beginning, we are started by using time series model, but when we see that was not working, we start to use summarized data, and the project starts to launch from there.
Any more questions? Oh, I have one. Did you get any kind of hardware bugs using this technique, or only software bugs? Can you differentiate between the two?
No, we cannot differentiate between the two. But yes, the model was capable to get kind of hardware failures because the software spans alert in the log when this kind of thing was happening, and the model was able to capture this kind of warnings.
Okay, more questions? I have another one then. I really thought of it. Let's say that now you said that the most time they were used, that was like spent, was about the guys who were trying to review those bugs, yes. Right?
Yes.
So let's say that I want to use that on open source software, because that's one of the biggest problems with open source software.
Yes.
How will you be able to translate this kind of modeling process to, let's say, Apache or Nginx or whatever?
Well, that's a really hard question, because the most important thing here, obviously, is the feature extraction. Is the feature that we are putting in the model, and these features were very specific of smartphones and very specific about Android even. So it would be a lot of work to generalize this model.
Okay. Any more questions? Okay. We have
one last question, yeah.
And that's the last question.
So, so did you have any problem with class imbalance? Because I understand that bugs must be rare. I think
30% of
30%.
bugs.
Oh, okay.
Exactly.
So it's not rare at all.
No, but balance was not an issue for us.
Okay, then. Let's thank again Ramon, please.